At some point in time, approximately 66 million years ago, a profound hush descended upon Earth. It was a silence left by the disappearance of the planet's dominant creatures. The seemingly eternal reign of the dinosaurs crumbled, and our world, for countless eons ruled by giant reptiles, endured one of life's most dramatic mass extinctions. This wasn't just a single event, but a cascade of cataclysms so profound they rewrote the fate of every life form, redefining the very course of evolution. Imagine the scene. Entire classes of living beings, thriving in diversity across land, sky, and oceans, were swept from the face of the Earth. Picture the pterosaurs, lords of the sky, or the colossal marine beasts like plesiosaurs and mosasaurs, terrorizing the seas. And of course, the vast tapestry of non-avian dinosaurs that inhabited every continent. They and countless other species were annihilated, erased from history in the blink of an eye, leaving behind a grieving world plunged into unprecedented chaos. For the fortunate few, or perhaps the unaware, who managed to escape immediate annihilation, life became a desperate battle for adaptation. The post-apocalyptic environmental conditions were brutal. Other life forms, driven by the sheer will to survive, changed so drastically, in ways so fundamental to their physiology, anatomy, and behavior, that they became almost unrecognizable from their ancestors. It was a race against time, where flexibility and the ability to adjust to the planet's new parameters were the only currency. The exact reasons for this tragic event, now universally known as the Cretaceous-Paleogene extinction event, are still under intense investigation. The predominant hypothesis points to a cataclysmic impact. A colossal asteroid, about 6 to 9 miles in diameter, colliding with the Yucatan Peninsula in Mexico, unleashed a sequence of apocalyptic events. This impact released energy equivalent to billions of atomic bombs. It launched a massive cloud of dust and debris into the atmosphere, blocking sunlight for months, perhaps even years. This resulted in an impact winter, with global temperatures plummeting, photosynthesis inhibited, and the food chain suffering a catastrophic collapse. Compounding this and perhaps exacerbating conditions was intense volcanic activity in the Deccan Traps, India, which released gigantic quantities of gases that further altered atmospheric and oceanic chemistry. As a direct result of this cataclysm, a staggering 3/4 of all living organisms on our planet simply ceased to exist. To put the selectivity and devastation into context, almost all animals weighing over 55 pounds perished, clearing the stage for a new era. The impact was comprehensive, sweeping away the great dominators and paving the way for new forms of life. This event was not merely an end, but a turning point, the close of the Mesozoic era, dominated by dinosaurs and reptilian life, and the dawn of a new and uncertain chapter in Earth's history, the Cenozoic. But what's most fascinating is what emerged from the ashes. The majestic dinosaurs, which held sway for 160 million years, gave way to creatures that, though initially small, discreet, and often nocturnal, would prove no less impressive and even more adaptable and innovative, the mammals. This is the Cenozoic era, the time we live in today, also known as the Age of Mammals. A colossal period of approximately 66 million years. That extends to the present day. It's divided into 3 major geological periods: the Paleogene, the Neogene, and the Quaternary. Each of these periods revealed dramatic shifts in climate and the geographical distribution of continents, alongside an explosion of biodiversity, forcing life to adapt in unimaginable ways and leading to the formation of the complex ecosystems we observe today. The big question is, how did these small beings, who for so long lived in the shadow of reptiles, not only survive the extinction, but find the opportunity to flourish? What challenges did they face on a constantly changing planet? What wonders evolved from their lineages? And how did this journey of tens of millions of years of adaptation and diversification bring us to the complex and dynamic world we know today. Prepare to unravel the mysteries, transformations, and resilience of a planet that reinvented itself, where life against all odds found a new path and prospered. Now that we understand the magnitude of the catastrophe that rewrote our planet's history, let's dive into the 43 million year journey of the Paleogene, the first and longest period of the Cenozoic era. It was a time of healing and transformation, where Earth's biosphere, wounded but resilient, recovered from the mass extinction. The Paleogene is divided into three crucial epochs: the Paleocene, the Eocene, and the Oligocene, each with its stories of survival, adaptation, and an explosion of evolution. Our journey begins in the Paleocene epoch, a period that spanned from 66 million to 56 million years ago. Imagine a world in convalescence, yet teeming with the potential for new life. The early Paleocene climate was more stable and significantly warmer than today, a true greenhouse world without polar ice caps. This age of warmth allowed vast tropical jungles to cover a substantial portion of the planet, extending to latitudes that are now temperate, like Antarctica and parts of North America. This abundance of vegetation created a humid, fertile, and resource-rich environment that would fuel the proliferation of new life forms. Earth's geography, though beginning to sketch the contours of the continents we recognize today, was different and constantly shifting. South and North America, for instance, were separated by tropical seas, acting as natural barriers that prevented species migration and fostered the evolution of unique faunas. The Indian subcontinent had just begun its slow march towards the Asian coasts, a collision that, in millions of years, would raise the world's largest mountains. And the ancient Tethys Ocean, shrinking due to the movement of the African and Eurasian plates, still separated Africa from Eurasia, preserving unique biomes and creating a complex dynamic of ocean currents and climate patterns. In this scenario of recovery and transformation, the abundance of plant food and the absence of dinosaurs allowed mammals, which previously lived in the shadows and in restricted ecological niches, to reproduce rapidly. They expanded into more areas, exploring the niches once dominated by reptiles. It was in this dynamic and opportunity-filled environment that the ancestors of most mammals we know today appeared, laying the groundwork for the vast diversity that would follow. In the warm, humid forests of the Paleocene, for example, the miacids prospered. These were small predators with agility and a build that resembled modern-day martens and weasels. Despite their modest size, generally no larger than a domestic cat or a small dog, they were successful in their environment, hunting small vertebrates and insects. Most importantly, the tree of life points to them as the probable ancestors that gave rise to the diversity of modern carnivorous mammals. Think of the entire lineage that came from them, from the powerful lions and bears, the agile wolves and foxes, to your own cats and pet dogs. Their adaptability in a world without the great reptile predators was crucial for the evolution and the dominance of all the carnivores that would reign in the Cenozoic's terrestrial food chains. But it wasn't only on dry land that mammalian life found new opportunities. It was also during this time that the first archaeocetes, the earliest ancestors of modern whales, emerged. And here's the surprise: the first archaeocetes, like the notable Pachycetus, looked nothing like whales. They were leggy creatures, more closely resembling hippos. Imagine that image, a calm four-legged all-terrestrial mammal that would give rise to the giants of the ocean. Pachycetus was probably an inhabitant of swamps and rivers, with a slender body and teeth adapted for catching fish. Although not yet fully adapted to aquatic life, being probable inhabitants of coastal and estuarine environments, their skeletons already began to reveal the first subtle adaptations for a semi-aquatic and eventually fully aquatic lifestyle. Modifications in their limbs, bone densification to aid in submersion, the structure of their respiratory organs, and crucially, the inner ear which already showed characteristics found only in marine cetaceans and are essential for hearing underwater, were the first hints of their inevitable and impressive transition back into the water, marking the first step in one of a mammal's most spectacular evolutionary achievements. And for us humans, the Paleocene is also a foundational chapter. Small primitive primates, similar to lemurs and tarsiers, made their discreet appearance during this period. They were nocturnal creatures, with large eyes and brains relatively larger than those of other mammals of the time. They were distinguished by their predominantly arboreal life, adapted to living and moving with agility in the canopies of the dense tropical forests. Their diets were varied, consuming fruits, insects, and leaves, which allowed them to exploit an abundant and safe niche. These early primates, however distant they may seem from us today in their forms and habits, planted the seeds of our own evolutionary lineage, showing that even the humblest beings, the underdogs of the dinosaur era, could contain immense potential. The mass extinction, however devastating it may have been paradoxically, was the catalyst that removed the old kings and freed up a vast array of ecological niches, a true invitation for mammals to flourish, diversify, and completely redefine life on the planet, paving the way for the era that would be theirs and ultimately ours. Now we fast forward to the Eteriocene epoch, a period that stretched from at 56 million to 33.9 million years ago. This was an era of exploding diversity, where mammalian life, already well established in the Paleocene, began to take even more impressive and often gigantic forms. The Eocene witnessed one of the warmest periods in Earth's recent geological history, surpassing even the Paleocene in temperature, with the Paleocene-Eocene thermal maximum being a notable highlight. During this peak, global temperatures rose dramatically, and the absence of permanent ice caps at the poles led to a much higher sea level than today. Tropical forests extended to latitudes that are now icy, such as parts of Antarctica and regions of the Arctic, creating a watery and densely vegetated world. As the climate warmed, the continental dance continued to reshape our planet. The outlines of the landmasses were already much closer to their current forms, but the collision of tectonic plates was at its peak. India, after its long journey, finally collided with the coasts of South Asia. This monumental collision unleashed geological forces, compressing rock strata into folds. This event marked the beginning of the uplift of the Himalayas, the largest mountain system on our planet, a colossal natural barrier that today profoundly influences Asia's weather patterns. This geological force, which remains active, shaped landscapes and influenced biodiversity on a global scale. Amidst these climatic and geographical transformations, Eocene mammals evolved into forms that, while some resembled their modern counterparts, others were surprisingly different. One of the most enigmatic and imposing inhabitants of this epoch was Andrewsarchus. This was possibly one of the largest carnivorous land mammals to ever exist. What we know about it is fascinating and limited, as the species is known primarily from a single and massive fragmented skull discovered in Mongolia. However, this skull is colossal, measuring 33 inches in length, which is approximately 1.5 times the size of a large grizzly bear's skull. Scientists estimate its bite was more powerful than any modern terrestrial predator, a crushing force capable of pulverizing bones, evidenced by the deep depressions in the skull that served as attachment points for the powerful muscles of the jaw. Reconstruction of this animal's skeleton suggests that its total length could have exceeded the 13 feet, and its weight could have reached up to 1 ton. But here's the most surprising part. Studies suggest that Andrewsarchus, apparently, belonged to the group of primitive ungulates. This means that its closest relatives were, shockingly, the ancient pigs, hippos, and even the first cetaceans. The structure of its teeth and the analysis of its few fossils indicate that most likely it was an opportunistic omnivorous predator. Unfortunately, the rarity of its fossils keeps many details of its life, its exact diet, and its kinship open for scientific debate. And if we're talking about terrestrial giants, the Eocene also was the birthplace of the first ancestors of what would become the largest land mammal of all time, Paraceratherium, often known as Indricotherium. Although its full form would only manifest in the Oligocene, its progenitors, like the Yuxia and Forstercoperia, were already beginning to emerge. These animals, related to modern rhinoceroses, but without horns, already showed the tendencies for the gigantism that would characterize their descendants. Their evolution reflects the abundance of food and the absence of predators capable of threatening them in their adult stage. In the marine environment, the evolution of primitive cetaceans continued at an accelerated pace. Species like Basilosaurus and Dorudon, which looked like giant sea serpents and were erroneously classified as marine reptiles by 19th century house scientists due to their elongated shape, were already completely aquatic. They represent a leap from their semi-aquatic Paleocene ancestors. With hydrodynamic bodies and vestigial hind limbs, an evolutionary remnant of their terrestrial ancestors, these creatures show the full adaptation to a purely marine lifestyle, hunting fish and squid in the vast oceans of the Eocene. These evolutionary and geological events, like the raising of mountain ranges, not only redefined the geography of the planet, but also influenced global climate and the formation of new habitats, opening paths for a diversification of life that was just beginning. Now we advance to the last and fascinating epoch of the Paleogene, the Oligocene. A period that lasted from 33.9 million to 23 million years ago. This was an era of significant climatic transformation, marking the beginning of a sharp global cooling, which contrasts dramatically with the warmth of the Eocene. The vast tropical forests that dominated the previous epochs began to yield ground, being replaced by grassy steppes. This cooling witnessed the beginning of the formation and expansion of the massive Antarctic ice sheet, transforming a once green continent into a cold desert of ice. Meanwhile, the incessant dance of the continents continued to redefine the world map. Australia, which had already separated from Antarctica, continued its isolation, allowing its fauna and flora to evolve into unique lineages of marsupials. Africa, in turn, continued its northward displacement, approaching the European continental mass. This approximation and subsequent collision of tectonic plates generated pressure on the Earth's crust, elevating mountain ranges and giving rise to the majestic European Alps, one of the world's most iconic mountain systems. Amidst these climatic and geological changes, the Earth was the stage for cataclysmic events that demonstrate the relentless force of nature. Approximately 26 to 28 million years ago, in the area that today corresponds to Colorado, in the United States, the supervolcano La Garita erupted. This was one of the largest volcanic eruptions of the entire Phanerozoic, the geological era that encompasses most of complex life on Earth. The scale of the destruction was astonishing. An area of more than 11,000 square miles, larger than the state of Maryland or the entire country of Belgium, was covered by a layer of hot ash and pyroclasts of about 100 meters in thickness. All life in the vast radius around the volcano was destroyed. However, even in the face of such devastation, the history of life shows us a fundamental truth. Nature can overcome any disaster, and life, with its incredible resilience, always finds a way to recover and innovate, filling the empty spaces that arise. It was in this time of great transformations, where the planet cooled and landscapes changed, that the Earth was inhabited by surprising animals, some as large as the dinosaurs that preceded them. A notable example are the Paraceratherium, ancient herbivores related to rhinoceroses, but that stood out for their gigantism. The largest specimens measured about 15.7 feet at the shoulder, which made them taller than a large African elephant. Thanks to their long necks, these giants could raise their heads up to an impressive 23 feet in height, reaching the highest foliage in trees that no other terrestrial animal could. To illustrate the scale, a modern rhinoceros would comfortably pass under the belly of its gigantic ancestor, and a human would barely be able to reach its knee. It was estimated that these giants could weigh up to 20 tons, which consecrates them as the largest terrestrial mammals of all time. To contextualize, even the largest sauropods, like the Brontosaurus, weighed only about 15 tons. Despite their gigantism and imposing presence, we still don't know many details of the exact appearance of the Minx Paraceratherium. Not a single complete skeleton has been found. We only have fragments, which makes a perfect reconstruction difficult. However, most scientists agree that despite their kinship with rhinoceroses, the Paraceratherium did not possess the characteristic horn, but might have had a small trunk, similar to that of tapirs, to assist in feeding. This adaptation would allow them to collect leaves from the top of trees, their main food source in vast forests and wooded areas. It is probable that these giant herbivores lived in small herds and led a nomadic lifestyle, continuously moving in search of food. Unfortunately, the magnificence and dominance of the Paraceratherium nasiais would not last forever. They became extinct at the end of the Oligocene, marking the end of a spectacular lineage. Scientists speculate that this extinction was a complex result of climatic changes that altered their habitats and, crucially, the arrival of new competitors and predators. Around this time, new large herbivores like the ancient elephants, which were more efficient in exploiting the vast steppes, penetrated their habitat regions, generating competition for food. In addition, large specialized carnivorous predators emerged, such as the hyenodonts and the amphicyonids, also known as bear dogs, which represented a threat to the young Paraceratherium. The arrival of these new inhabitants of the Asian steppes altered the balance, placing the Paraceratherium in competition for food and under new predatory pressure. The scarcity of resources and the threats from the new inhabitants led little by little these giant herbivores to their extinction. But the Oligocene was not just the era of the Paraceratherium. Between the 37.2 million and 28.4 million years ago, another group of large carnivores prospered, the Entelodonts. These animals are a paradox of evolution. Although their appearance resembled that of large and ferocious wild pigs, with long snouts and prominent bony protrusions on the skull and jaw that earned them the nickname hell pigs, evolutionarily, they were much closer to hippos or even to cetaceans. They were impressive creatures in size, measuring up to 2 meters in height at the shoulder and weighing over 1 ton. The head, which could be 1 meter long, housed an enormous mouth replete with sharp incisors, long pointed canines, and broad and flat molars, indicating an incredibly diverse diet. Most likely, entelodonts were highly opportunistic omnivorous creatures, with a strong tendency towards predation of large animals and necrophagy. Despite their massive size, they were surprisingly capable of developing considerable speed, which made escape an almost impossible task for their prey. A wild boar the size of a large bull, which preferred to feed on meat, represented a serious threat to any terrestrial inhabitant of the time. It is not surprising that entelodonts fought successfully and dominated their ecosystems for so long, with fossils of their lineage being found throughout Eurasia, demonstrating their vast distribution and evolutionary success. Leaving behind the millions of years of the Oligocene, marked by cooling and the rise of new life forms, we enter now the Neogene period. A crucial phase that extended from 23 million to just 2,580,000 years ago. This period is notable because our planet assumed a form and appearance practically indistinguishable from the present. The continents finally occupied their current positions, and most animals and plants began to resemble what we recognize today. The global climate of the Neogene continued its gradual trend of cooling and drying, initiated in the Oligocene, although with fluctuations. The average global temperatures decreased, and the expansion of the vast grasslands accelerated, supplanting many of the dense forests. The polar ice caps grew significantly in the Arctic and Antarctica, and the end of the period was marked by an intensification of glaciations, foreshadowing the ice age that would follow. These environmental changes propelled new waves of adaptation and diversification in wildlife, forcing species to evolve or perish in increasingly challenging environments. In the midst of these planetary transformations, the Earth was inhabited by an incredible variety of creatures, both in the oceans and on dry land. In the depths of the ocean, a terrifying and unrivaled predator reigned absolute for millions of years, the megalodon. This giant shark, which could reach to 15 meters Gauss in length and weigh 35 tons, was the apex of the marine food chain. Its bite was incomparable, capable of crushing the largest bones of whales and other marine creatures of its time. The megalodon was not just a great predator, it was the king of the depths, with a domain that lasted for millions of years before its eventual and still debated disappearance. On land, the evolution of mammals continued at an accelerated pace, filling the ecological niches created by the new grassland landscapes. A diverse and fascinating group were the Gomphothes, close relatives and ancestors of the current elephants. A distinctive feature of many of their species was the presence of 4 tusks, 2 in the upper jaw and 2 in the lower, which they used to excavate roots, strip trees of their leaves, or in territorial disputes. Their size varied enormously. Some could exceed the dimensions of a modern African elephant, with more than a 4 meters arm in height, while others were much smaller, demonstrating the versatility of their lineage in adapting to different environments and diets in almost all continents. The Neogene was also a period of crucial geographic events that profoundly impacted the distribution of species and the interconnection of the continents. The opening and closing of straits, such as the Bering Strait, which connected Asia to North America at different times due to sea level fluctuations, allowed massive migrations of fauna between the continents. These land bridges functioned as biological corridors, facilitating the interchange of species and remodeling entire ecosystems, leading to new competitions, diversifications, and sometimes local extinctions. Notable evolutionary advancements, which touch us closely, also occurred in this period. The great primates continued their diversification, with lineages separating and evolving in different directions. In Africa, the emergence of the first hominins marked the beginning of a lineage that would lead directly to modern humans. These primitive ancestors, such as the Sahelanthropus and the Orrorin, adapted to the expanding savanna environments, beginning to develop crucial characteristics such as bipedal posture, which offered advantages in the search for food and in the detection of predators and the manipulation of objects, fundamental for the development of tools. With the growth and proliferation of the vast global grasslands, the coevolution of grasses and herbivores reached a new level of complexity and interdependence. Animals such as camelids, primitive horses, and rhinoceroses developed specialized teeth for grazing and more efficient digestive systems for processing grass cellulose, further driving the expansion of these new ecosystems that today dominate vast areas of the planet. Finally, the last epoch of the Neogene, the Pliocene, which lasted from 5,300,000 to 2,580,000 years ago, served as the crucial scenario for what was to come, a preparation for the Ice Age and the rise of humanity. Glaciations became more frequent and severe, with the growth of the polar ice caps affecting climatic patterns and global oceanic circulation. Geographically, the formation of the Isthmus of Panama, a land bridge that emerged slowly from the ocean, was a transformative event and of enormous biological consequences. This new connection, which united North and South America, triggered what is known as the Great American Biotic Interchange. Massive migrations of animals occurred in both directions, with species from North America, such as carnivorous mammals, camelids, horses, and elephants going south, and South American species such as giant sloths, giant armadillos, and carnivorous marsupials migrating north. This collision of faunas, although it led to new competitions and an explosion of diversification in some lineages, also resulted in the extinction of less adaptable species that could not compete with the new invaders. In this period, the discussion about our own cousins and ancestors is essential. Species such as the Australopithecus, for example, lived in Africa, showing characteristics that were increasingly closer to humans, such as the ability to walk upright consistently and possibly the use of primitive stone tools to process food. At the end of the Pliocene, most of the mammalian families that we know today, from the majestic felines and canines, passing through the large bovines and cervids to the small rodents, were already well established and highly diversified, with many modern species beginning to take shape. The stage was set for the arrival of the newest and, by far, most impactful evolutionary force on the planet, humanity. Leaving behind the millions of years of the Neogene, replete with diversification and consolidation of the continents, we now arrive at the Quaternary period. This is the most recent chapter and, for us, the most relevant in the geological history of the Earth, beginning about 2,580,000 years ago and extending to our present day. The Quaternary is distinctive for two monumental characteristics. It was the era of the appearance and development of Homo sapiens and its ancient hominin ancestors, and it was also a time of relentless cycles of glaciation and interglaciation which transformed entire landscapes. During the glacial phases, thick layers of ice covered vast portions of the northern hemisphere, extending across continents like North America and Eurasia. These masses of ice trapped large quantities of water, resulting in drastically lower sea levels, at times up to 120 meters below current levels. This exposed continental platforms and created land bridges, such as the famous Bering Strait, which allowed massive migrations of fauna between the continents. In the interglacial phases, the ice retreated, the seas rose, and the planet experienced periods of warming. Within the Quaternary, the whole Pleistocene epoch, which lasted from E2,580,000 to just 11,700 years ago, is popularly known as the Ice Age. This was a time where life adapted to extremes of cold and aridity. The megafauna, that is, the large animals, prospered in the icy steppes and in the temperate forests that characterized much of the period, exhibiting incredible adaptations to the cold environment and seasonal food scarcity. Think of the iconic mammoths and mastodons, which with their massive bodies covered by thick fur and their gigantic tusks dominated the icy landscapes of Eurasia and the Americas. They were colossal herbivores perfectly adapted to scrape-resistant vegetation under the snow and ice, utilizing their tusks and trunks. They played a crucial role in the engineering of the Ice Age ecosystems, felling trees and keeping the grasslands open. But these were not the only giants. In South and North America, from 2 million until approximately 12,000 years ago, the Megatherium inhabited a giant ground sloth that was an impressive spectacle, with a weight that could reach up to 4 tons and a body of about 6 meters. In length, the Megatherium was no smaller in size than an African elephant. The most fascinating is that, although it was a sloth, its main locomotion occurred on its hind legs, in a partial bipedal posture, using its enormous curved claws not only to pull leaves from tall trees, but also to defend itself from predators like the saber-toothed tigers. In Australia, in turn, lived the tapitan diprotodon spe from 1,600,000 to approximately 40,000 years ago. They were the largest known marsupials, surprisingly close to our current wombats and koalas, but on a gigantic scale. Some of these creatures reached 3 meters in length and 2 meters in height at the shoulder, weighing about 3 tons. They were colossal herbivores, as large as some hippos, that inhabited the woodlands and the grassy coastal plains that abounded in Australia before the arrival of humans. Besides these, the Ice Age was home to other spectacular predators and herbivores, the Smilodon, the famous saber-toothed tiger, with its terrifying fangs and an incredibly strong bite. The short-faced bear, one of the largest terrestrial predators that ever existed, capable of reaching more than 3.5 meters in height when it stood up, and the robust, woolly rhinoceroses, covered in dense fur to withstand the extreme cold which grazed in the tundras and cold steppes of Eurasia. And in the middle of all this, the great narrative of our own species unfolded. The Pleistocene marked the ascent and dispersal of our ancient ancestors. Between 1 million and 100,000 years ago lived the Gigantopithecus, a species known as the giant hominids. With an estimated height between 3 and 4 meters and a weight that could exceed 500 kilograms, these creatures were primate titans, inhabiting the dense forests and mountains of Asia and being closely related to modern orangutans. Obviously, given their mass, the Gigantopithecus could not climb trees with the agility of other smaller hominids. However, we know that part of their population lived in mountainous environments, taking refuge in caves and natural crevices. It is believed that their main diet included large quantities of bamboo, but the discovery of herbivore bones with tooth marks in Gigantopithecus lairs suggests that these creatures were, at the very least, omnivorous, taking advantage of carcasses or hunting smaller animals. The skeletal structure of the Gigantopithecus is similar to that of the gorilla, which means that most likely they moved primarily with 4 extremities in a form of locomotion known as knuckle walking or knuckle walking. Furthermore, these hominids possessed a relatively large brain volume for their time, which implies a comparatively high intelligence and, potentially, the ability to build and use primitive tools, although we do not have direct evidence of stone tools created by them. Unfortunately, the number of these giants decreased drastically with the propagation of the ancient ancestors of modern humans. Approximately between 100,000 and 300,000 years ago, they finally became extinct, leaving a mystery that the few fossil remains of Gigantopithecus continue to challenge scientists to unravel. The Pleistocene also was a period of coexistence and complex interaction between different species of the genus Homo. Homo erectus, known for its expansion out of Africa, the robust Neanderthals adapted to the cold of Europe and Asia, and the enigmatic Denisovans who coexisted and at times interbred with Homo sapiens before their own extinctions. This era of giants and of our ancestors showed us a vibrant planet and full of life. And it is here that our story becomes more intricate, and human intervention begins to shape the destiny of other species irreversibly. When primitive human tribes spread across the earth, they not only prospered and adapted, but also, tragically, contributed to the destruction of many other creatures. The efficiency of human hunter-gatherers, with their tools and cooperative strategies, represented a new predatory pressure. One of these victims was the Pran megatherium. Its relatively easy life, without great predators capable of threatening an adult of its size, came to an end about 15,000 years ago, when the first nomadic and skilled human hunting tribes arrived in South America. The strong but clumsy and giant megatherium was defenseless against the sharp spears and arrows, and its population soon reduced to 0. Other giants that are believed to have disappeared from the face of the earth, at least in part, because of human intervention, were the Diprotodons esos of Australia. Their extinction on the Australian continent notably coincides with the arrival of the primitive human tribes about 40,000 years ago. However, the scientific debate about the exact cause of their extinction is complex. Some scientists suggest that human hunting by itself was not the only cause, but rather a factor added to environmental changes. It is postulated that an anomaly in the Earth's magnetic field that coincided with a local decline in temperature and conditions of extreme aridity could have weakened the populations of Diprotodons. The increase in natural radioactivity, together with this wave of cold and drought, would have slowed the growth of plants, causing widespread starvation to the massive herbivores. In this already weakened scenario, the impact of human hunting, even if it was not the only factor, would have been the final blow leading to the complete extinction of these magnificent marsupials. This is a crucial reminder that the history of extinction is rarely simple, involving a complex web of environmental, climatic, and biological factors, with human action frequently acting as a decisive catalyst. We arrive now at the human era, the Holocene epoch, the most recent and directly relevant chapter in the geological history of the Earth. This period began a mere 11,700 years ago and extends to our present days. The Holocene is unequivocally marked by the development of human civilization. From here, Homo sapiens, driven by an unprecedented cognitive and adaptive capacity, spread to every corner of the planet, not only adapting, but also shaping and transforming the environment. This ascent led us to occupy a dominant position, a position of power and influence that no other species has ever achieved on such a global scale. However, this meteoric and apparently triumphant ascent has a dark side. The other side of this development has been technological disasters and changes, often irreversible, in the biological and ecological balance of the planet. Think of the vast forests, such as the Amazon and the tropical forests of Indonesia, that disappear at an alarming rate to make way for agriculture, livestock, or resource exploitation. Think of the rivers, once clear, that become industrial and urban sewers, suffocating entire ecosystems. Think of the plastic pollution that today permeates our oceans, forming islands of trash that threaten marine life. Human activities since the Industrial Revolution have contributed alarmingly to the increase in the concentration of greenhouse gases in the atmosphere each year. The burning of fossil fuels, coal, oil, and natural gas, for energy, transport, and industry, together with deforestation, has released billions of tons of carbon dioxide and other gases that trap heat. This accumulation has a direct impact on the global climate, leading to the warming of the planet, the melting of the polar ice caps, the rise in sea level, and more frequent extreme climatic events. The consequences are global and devastating for all inhabitants, including ourselves, with food security, water availability, and public health being severely threatened. It is with a pang of sadness and urgency that we note that the animals that inhabit the Earth are increasingly less numerous. Global biodiversity is in decline. It is painful to realize that often their death and the disappearance of species are caused not by natural events but directly by human action. Excessive and illegal hunting, the irresponsible use of land that destroys habitats, environmental negligence, and the inability to act in the face of climatic changes have already led scientists to register what is frighteningly familiar, but this time with our signature: anew, the sixth great extinction of species. And the most worrying thing is that this extinction, driven by our actions, has consequences as serious and comprehensive as the 5 previous extinctions. Our own history, the one we have just explored, full of cataclysms, rebirths, and adaptations, now serves as a mirror and a warning. What can we learn from past eras about the resilience of life and the vulnerability of ecosystems when confronted with drastic changes? Facing all this, we are confronted with deep and existential questions without easy answers that resonate with the uncertainty of our future. Will humanity, in its incessant search for progress, find a path to sustainability, to harmonious coexistence, before causing irreversible damage to the only home we know? How long will it take for our planet, with its extraordinary capacity for recovery, to heal from the devastating effects of our technological progress? And will nature, in its infinite creativity and persistence, generate new forms of life once it has overcome this crisis, just as it overcame the previous ones and saw mammals emerge from the ashes of the dinosaurs? It is unlikely that anyone can answer these questions with certainty, but history shows us that action is always more powerful than inaction. However, there is something crucial that we can do. each one of us. If the themes we discussed today resonate with you, if this journey through the history of the Earth made you think deeply, surprised and informed you, please help us spread this vital message. Comment on this video with your reflections, share it with your friends and family, and leave your like if the content was interesting and valuable to you. Know that we dedicated a lot of time and effort to make each episode not only interesting, but also informative and engaging, bringing this complex knowledge to you in an accessible way. Your support is immensely important to us. It is what drives us and motivates us to continue this journey of discoveries and to share more incredible stories about the evolution of life on our planet. Stay tuned for more fascinating and revealing journeys through the history of life on Earth.